Hello. We are continuing our introduction to physics-informed machine learning. But in the first series, as I mentioned before, we are putting aside the physics-informed component. We are just focusing on the machine learning itself. And here, we're going to go over two main branches of machine learning we're going to use in this course. Imagine you have done some tests, and again, you're varying an x parameter and you're measuring a z value. And you're trying to fit a model that describes the data. It's a regression problem. It's a regression approach to machine learning. And that's an outcome we would like to have in this example. So you might decide to either train what we call a deterministic machine learning model, like a neural network, which would be basically a closed-form solution that fits the data. And we're going to go over the neural network in this section specifically. Or you might decide to go into a more probabilistic approach, which means that at any given point, you're not saying by certainty that this is the underlying behavior, but you're presenting it as a probabilistic outcome. So where you have data, you have high confidence in the behavior of this underlying function. So you can see that your confidence level is high and you don't have much variation in the data. But as you move away from data, your prediction confidence should drop. And that's the main difference between these two approaches. This higher approach gives you a function with a prediction, specific predictions. Even for the area that we don't have data, this is the prediction of this approach, which might be useful in some cases, might not be useful if you don't have data in a certain domain, in a certain part of the domain. In this part, you're not saying by certainty that this is the outcome. You're saying, I think this is the average response, but there's actually an upper bound, lower bound confidence interval that I'm going to attach to that. So that becomes a probabilistic approach. So we're going to go over the basics of neural networks, and for probabilistic approach, we're going to go over the basics of Gaussian process regression. In this lecture, we're going to go over the neural networks, and the next lecture, we're going to go over the Gaussian process regression. So just some terminologies if you're not familiar with neural networks. You have a series of inputs or features. In this example, you have 3 inputs that you're varying in experiments, x1, x2, and x3. There is an output that you're trying to predict, z, a function of these 3 inputs. We call it outputs here. And then you construct an architecture. If you haven't seen this architecture, it has some initial features. And then you have some hidden layers which are, we're going to explain what those are. So there are 3 hidden layers in this case, just to learn the terminologies, and every hidden layer has 5 nodes. And there are some lines, the blue lines, that are connecting these nodes, and you will see later that there are some weights attached to those lines. So putting aside the complexity of neural network, the whole thing is that you have a bunch of inputs, and you are fitting a closed-form equation to predict the outcome as a function of those inputs. So that's the basics of the neural network approach that we're going to learn. So think about it as a closed-form equation that is fitted to data. The baseline calculation is like this. You have a bunch of inputs, x1 to xn. Typically, we add a constant 1 to the mix as well. Then you connect these inputs with some lines to a node, which every line has a constant attached to it. We call them weights, W0 to Wn here. In this basic calculation, you take the inputs, you multiply them by weights, and you calculate the weighted summation of all the inputs. One of the inputs is 1, so you will end up with one constant, W0. And then you have the summation of the other ones, which is W1 times Wi times Xi. So you do a weighted summation of everything. And then you apply a function to that weighted summation. We call that, the activation function. So in terms of terminologies, there is an activation function that is applied on the weighted summation. there is this constant which is attached to the input 1, and we call that bias, and then there's these weights. The whole idea of training a neural network is to find those weights, unknown weights, which are the constant of that closed form equation. So this is one layer calculation. I can make it more complex by adding a second layer now. So now the z is a function of a bunch of middle parameters, y1 to yn. And those functions are all functions of initial inputs x1 and xn. It makes it easier if you go in a back propagation, from backward calculation. So z is the function of all the y's and all the constants, phi0 to phi n. So there is one baseline calculation done at the here. And then every y is a function of x's. So this becomes a function of a function. So z is a function of y's, y's are a function of x's, and there's all of these lines that are connecting these nodes, and there are unknown constants attached to these lines. And again, the whole premise of training a machine learning model, in this case training a neural network, is finding these weights. Here is a more complex example. You have 3 inputs or 3 features. You have 5 hidden layers. Each hidden layer has 25 nodes. So you have 125 nodes in the middle, plus all of these biases that are added on top, 1 node for bias on top. And then you're predicting one output. This is, in a way, a closed form solution that predicts the output, one output, as a function of 3 inputs. But it does a lot of calculation in the middle. And if you look at what it does, this last node, which is the output, is a function of the last hidden layer. That last hidden layer is a function of previous hidden layer. That is the previous hidden layer function, so on and so forth. So this becomes a function of a function of a function. It's like you're going deeper and deeper and deeper into a function. That's why sometimes we call it deep learning. And if you count how many lines we have here, it represents how many constants you have to fit, or how many constants your closed form equation has. In this case, the closed form equation has close to 2,700 constants. So the process of training this machine learning model is basically finding all of those 2,700 constants through some optimization algorithms. Compared to a simple polynomial fitting, when you have 4 or 5 or 6 constants you're trying to fit, this becomes an extremely complex function you're trying to fit into given data. One other terminology I'm going to go over are activation functions. So I mentioned that in every baseline calculation, you take the summation of the weighted summation of the inputs, and then you apply a function on that, which we call activation function. There are many types of activation functions, and we are not going to go into details of those. I've selected 3 of them, which is ReLU function, sigmoid function, and tan hyperbolic function. We're going to use ReLU and tan hyperbolic a lot more in this course, but you can see the basic plots of the ReLU and tan hyperbolic. Tan hyperbolic is basically a tan hyperbolic function, as you can see here. ReLU function is a very simple function. It says if z is less than 0, assign a 0 value to the outcome, and if z is more than is a positive value, is equal to the input. So it becomes a max of 0 and z as the ReLU function. And I've also plotted the derivative of this function, which becomes important when we go over the optimization. Again, what I'm trying to do in this section is to go over many terminologies without going too deep into any of them. Once you go over the code, which is a simple example code I'll explain to you in a second, it becomes quite meaningful that you can set any of these parameters as a variable in training a machine learning model. Okay, so what's the simple example we're going to use for neural network? And again, this simple example shows you what is the true power of all of this hyperparameter optimization. When you're setting the number of nodes, when you're creating architecture, what's the effect of that? So there is an neural network intro Python code that you can use to go over all of these details. But the goal here is this. We have quadratic function is a simple quadratic function. And we're trying to train three neural networks to compare them to predict y, in this case, as a function of x, or as we call it, z as a function of x. And in first case, we're going to use a very simple architecture. It's just one input, which is x, goes into a middle layer, and then goes into an outcome. So it's like a one hidden layer with one input. And there are basically two weights that you're trying to find, plus the weights that will be four weights, to fit the data. Then you make the model a bit more complex by adding two layers, two nodes per layer. And then we're going to make it even more complex by saying we have three layers and then three nodes per layer. As we make them this equation more complex, which means that we are adding more constant to this equation, how does it become better in capturing a simple equation? And you can set all of these in the Python code provided for this section. And again, I'm not going to go into details of the code in the introduction. We will do that in the later case studies. So here are 6 results. When you're running the code, you can set the activation function, and you can set the number of hidden layers and the number of nodes per hidden layer. So you can see vertically, we have the first simple model, then the second more complex model, and then the third model. And then horizontally on the top row, we have ReLU function, and then we have tan hyperbolic function. The red curve is what we're trying to capture, and the yellow curve is the prediction of the neural network after it was trained. So the ReLU function and tan hyperbolic, when you have just one hidden layer, are simple to understand. It's like you either have a line or you have like an exponential function you're trying to fit into data. As you start adding more layers and nodes, it's like adding more of those base functions and trying to capture it. You can see that eventually, if you add a lot of nodes, a lot of layers, you can capture very complex shapes with ReLU, which basically trying to piecewise together some linear functions and capture any complexity. Tan hyperbolic is trying to do that with exponential functions. And that's the true meaning of increasing the complexity of your model. Even though it might not look very efficient in capturing this baseline curve, but the more you add nodes and layers, it becomes very effective in capturing any behavior that you want. One thing to pay attention, if you run the code many times and you look at the outcome, like for example, in this case, the most complex function, 3 by 3, 3 hidden layers and 3 nodes per hidden layer. These are 3 outcomes that we got by running the Python code just over and over and over again. Each time you will get a different results. So the results of a trained machine learning model are not unique. And we're going to learn why they are not unique. Mathematically, we say this is not a well-posed problem. There's no unique solution when you solve it. And you're going to see that intuitively why that's the case. But that also gives you a pause. When you say I have a trained machine learning model, there are some limitations that comes with that. Specifically, it's very difficult to extrapolate beyond the training zone if you're not enriching it with physics, as you're going to learn later. But you can also see that even though some of the functions might be similar, some of them might be too far off. Okay, so why is that? Why is it that you have non-unique solution, and why is it that sometimes we get better results than other results? To learn that, you have to understand what are we trying to do during training a machine learning model. Here it shows that schematically, you have your initial curve, which are the pink dots, and then you have your predictions of the machine learning model, which is the yellow dots in every step. There's some errors between these pinks and yellow dots in every locations. In every iterations of training, you calculate an error value. We call it loss here. This loss is root mean squared error, which is you get the error values, the average of them, and then root mean square becomes the root of the squared errors. So this is one loss function you can define. You can define many other loss functions. But the aim is to minimize this loss function through some algorithms. Why is it that if you run the machine learning model, every time you train a machine learning model, every time you might get a different outcome based on a single loss function? I'm not going to go through the details of this. Just for your information, there is this algorithm which is called backpropagation, and there is some optimization algorithm which basically takes the derivative of outcome with respect to the weights of this unknown function, and in every iteration tries to minimize the gap between the predictions and the true function. Again, if you're interested, you can look more into that algorithm, backpropagation, optimization. I think it's beyond the scope of what we're trying to learn here. But I'm going to show you what it means with a very simple example. And this is the intuition behind why you get non-unique solution every time you're training a machine learning model. Imagine you have a simplest neural network. There's one input, x. You multiply x by a constant, W1. Then you get to a middle layer, y. You apply a tan hyperbolic function to y. Then you multiply that y by W2. And you apply another tan hyperbolic function to get z, which is the outcome. So this is a neural network which has one input, one hidden layer, one node per hidden layer, without any biases, and one outcome, only two constants that we're trying to modify to fit the data. So this equation here, z, is tan hyperbolic of W2, tan hyperbolic of W1, x, is the closed form equation for this neural network. Imagine that I've given you only 1 point. I say the only thing we know is that when x is 0.5, z is 0.5. So what you're trying to do is calculate an error value between the prediction, which is z of this function, and 0.5. So the prediction becomes like this. You say, I have an error, the loss, which is 0.5 minus the prediction of neural network at given value of x equal to 0.5. So the loss function, the error value you're trying to minimize is 0.5, which is the outcome, the z, minus predictions of neural network when x is 0.5. And it becomes this function. So the whole idea here is to minimize this function using some algorithms by varying W1 and W2 until you get something very close to 0.5. So let's plot that loss function and see what are we trying to do. This shows when you're changing W1 and W2, what is the shape of the loss function. And again, the loss function is given here for your own reference. So by changing W1 and W2, you get different error values. The whole approach here is to find a combination of W1 and W2 with this error value becomes very small or gets minimized. If you look at the shape of this loss function you're trying to minimize, if you select W1 and W2 at the corner, the error is very high. And then iteratively, you can start changing those constants such that the error value drops. You get this saddle-shaped points typically that some algorithms may get the stock here, and they give you that value as the best combination of W1 and W2. But you can see that there are some areas where you have lots of local minimas typically gathered together. And then you have some plateau regions when the loss function doesn't change much. If you're lucky when you're training a machine learning model, you will end up with one of those local minimum values. But you can see that there are many combinations of W1, W2 that minimizes the error. But that means that you have many solutions that comes out of this. So sometimes you might start an iteration and you might end up with something like here, which is a combination of W1, W2 that minimizes loss. And sometimes you might end up at this other corner, and sometimes in the middle. So there are no unique solution that minimizes the function. Sometimes if you're not lucky, the algorithm gets stuck in this plateau regions, which means that it tries to change W1, W2 iteratively to change the loss, but the changes are so minimal that it might assume that, oh, we arrived at an optimal location. So it might stop the process. The point that I want to emphasize here is that when you train a machine learning model, there's no unique solution because the loss function you're trying to minimize doesn't have one single minimum location. It has many local minima values. Okay, so we are going to stop here, and in the next lecture, we're going to go over the baseline, another baseline machine learning approach is the Gaussian process regression.